So let's talk about what is gravitational potential energy. So the symbol we're going to use is U lah. So they use the symbol U to represent gravitational potential energy. Now when you were in Form 5 and also your AS, right? We used to define gravitational potential energy as what?
Energy position.
Energy possessed by a body due to its position in a gravitational field. Understand? That's your AS definition. Meaning to say, the higher it is in the gravitational field, for example, like on the surface of the Earth, you have the lowest potential energy. You go further, higher and higher, you get higher and higher gravitational potential energy, right? That's what you use to take in AS lah. But we also used to take which point to be the zero GPE. Where did you assume to the zero GPE to be? At the surface of the Earth, right? At the ground level, right? So based on our definition, it means that at the surface of the Earth, it has no more potential to do work. Correct? So does it mean that if I dig a hole in the ground, it won't fall? It will still fall, right? So this means to say the zero GPE is not the surface of the Earth. So some people said the GPE of the Earth is when it's zero, is at the center of the Earth lah, which is also wrong. I'll tell you why later. The actual zero of GPE is actually at infinity. That means if this is the Earth, at infinite distance away from the Earth, the GPE is zero. Why? Because at infinity, will there be any more force pulling the mass back? Because when your R approaches infinity, what will happen to the force? Approaches zero. That means it will no longer be attracted to the Earth, so it will never come back. So at infinity, the GPE is zero. But then again, we know that if you take an object from the surface of the Earth, let's say on the ground, you lift it up a bit higher, the GPE will increase or decrease? Increase. If you bring it even higher, the GPE will keep increasing, right? So when you bring it all the way to infinity, the GPE becomes zero. So how do you manage to increase the GPE to become zero? You can do it if you take all the values of GPE to be negative. So let's say at this point here is negative 10. If this is negative 10, you bring it to negative 3, did it increase or not?
Yes.
Because negative 3 is bigger than negative 10. So it keeps increasing until you reach a maximum value of 0. Therefore, all values of GPE are supposed to be negative. There's no such thing as positive GPE. Why? Because the highest value is 0. Do you understand? But what would the GPE be at the center of the Earth? It will be the most negative. So let's say negative 300, let's say. Because it is the lowest, it cannot fall anymore. So it is correct. When you reach the center of the Earth, the object won't fall, right? But it doesn't mean that it's a center, it has 0 GPE, but it has the lowest GPE. So lowest means cannot fall anymore. Yeah? So all values below infinity must always be negative. Do you understand? So why is it in your Form 5 or your AS, your GPE is positive right now? You always count your GPE as positive. Do you ever take it as negative? No, because you need to understand. The formula for GPE that we used in AS and also in your Form 5 is what? Now, this is not actual GPE at a point. This is actually difference in GPE between 2 points. When you use MGH, you are not calculating the GPE here as negative 10 or here as negative 3. But what you're doing is the H represents the difference in height between these 2 points. So you're calculating the difference in GPE between 2 points. So when you calculate these 2 points here, let's say this is negative 10, this is negative 3. So what is the difference?
7.
So you are calculating this as 7. So it doesn't give you the GPE at the point here or here, but it gives you the difference between 2 points. So the formula for GPE, you don't have to derive it, but you need to, if you're interested how they derive it, they actually find the work done to move an object from this point to infinity. Let's say I bring this mass from here to infinity, I need to do 3 joules of work. So then the GPE here is considered to be 3 lah. So how you find the formula is you need to integrate F dr. Because you know why? The force is a function of distance, gmm over r squared. So you cannot take force times distance to find work done. Force times distance to get work done is only for constant force. If the force is not constant, you must find the area under the graph to find work done. That's why you must integrate F dr. But it's because it is not in your syllabus, you don't have to know how to derive. The formula is negative gmm over r. So that is the formula for your potential energy for gravitational fields. Then people ask me, why is this formula negative gmm over r so much different from mgh? Now, negative gmm over r is the potential energy at this point if you substitute the r from here to here. Negative gmm over r is the potential energy at this point if you substitute the r from here to here. But if I minus these two, I take this minus another value, I will never get mgh, right? So why? Because this formula is just an approximation of the correct way of calculating change in GPE. The actual way of calculating actual change in GPE is to use this formula, substitute the r from here to here, which is the higher potential energy, then use this formula again to find the potential energy from here to here, which means you must find the r from here to here, and then you need to subtract. But for small distances, the field strength is fairly constant. So mgh is an approximation of the correct way of calculating change in GPE. So how small is the distance involved before you can assume the field strength is constant? For distances less than 1,000 meters. Then the field strength is considered to be fairly constant, so we can use mgh to calculate the approximate change in GPE. But if you want to find the exact value of the change in GPE, you must use this formula twice. For distances more than 1,000 meters, you cannot use this anymore because the field strength, the difference in the value of field strength is bigger and it will no longer be assumed to be constant. So you will get a very much different value if you use this and you use this twice. For less than 1,000 meters, if you use this and you use this twice, you get almost the same answer. So because when you were younger, you were not wise enough. You were not ready. So they gave you this formula as an approximation. The correct way is always to use this. Do you understand? Okay, so we'll stop here and then we'll go on to the next slide. So the definition of GPE will be like this. The GPE of a mass at a point in the gravitational field is defined as the work done in bringing the mass from infinity to that point. So that's the definition. So why is the definition so weird? I explain to you why. Now let's say the object is at point A. Let's call this point A. If you want to bring the object to infinity, how much work must you do? This is negative 3 joules. This is 0 joules. So how much work must you do? 3 joules. So if I do 3 joules of work on this, or on a test mass here, to bring it to infinity, it will reach, the work done is 3 joules. But if, let's say, I want to allow the mass to return back to the same point, I don't have to do the work because the forces are supposed to be attractive, right? So if I let go, give it a slight nudge, so as it moves towards point A, who does the work? I do the work or the system does the work? And how much work will the system do to reach back point A? Also 3 joules. But the difference is, this is work done by the system. So work done by the system is negative, work done on the system is positive, remember? So to define these 3 joules here, but I need a negative because all GPE, remember, is supposed to be negative. I can either define as work done to bring this mass from this point to infinity, or work done to bring the mass from infinity to the point. But which one will give a negative work done? I move it to infinity or infinity move there? So therefore we define GPE as work done in bringing the mass from infinity to a point in the field. That's the definition of GPE. Understand? So what is gravitational potential? Now gravitational potential is, you can take the formula for potential energy and divide by mass. So in other words, when you define gravitational potential energy, you modify a bit, you get the definition for potential lah. Do you remember what's the definition for gravitational potential energy? Yeah. So when we talk about potential, the definition of potential, just modify a bit. So the definition of GPE will be work done in bringing the mass from infinity to that point, right? So definition of gravitational potential will be work done in bringing unit mass, because you do it by m, from infinity to that point. So the only difference is unit mass. Change the mass to unit mass. Okay, so that's the definition of potential. So what about the formula? The formula, since your GPE is negative GMM over R, you divide by a mass, wouldn't one of the mass cancel? Okay, anyway, this is not alpha, this is times. So one of the mass will cancel and you get negative GM over R. So now you have two formulas for potential. One is potential energy divided by mass, one is negative GM over R. Now, potential and potential energy are vector or scalar quantity. Potential energy is vector or scalar? Scalar. So potential is also scalar. So therefore, the negative is super important. You must not drop the negative. You must keep the negative. So the negative here must be kept there because we know that the maximum GPE is 0 at infinity. So the maximum potential is also 0 at infinity. So all the values will be less than 0. So you must have a negative. Now, then the next thing is, when comparing these two equations, only got one mass here. So what mass do each of these mass represent? If the m is at the bottom, it must represent the test mass. If the m is on top, it must represent the mass that produces the field. Example, if let's say we are talking about the Earth here, and we take a point on in the field, let's call it point A lah. So when you say bring unit mass from infinity to that point, that means it's 1 kg, agree or not? So if I use this formula, U over M, the U will be the potential energy of this test mass, which is, let's put the test mass there. And then the M will represent the mass of the test mass. But if I use this formula to find the potential of the Earth at this point, then the M here is just the mass of the Earth, R is distance from here to here. Now, what is the significance of potential? Because some people don't get what is the importance of potential. Potential is important to you exactly as how field strength is important to you. You see, force and potential energy are very similar in the sense that force depends on the Earth's mass and also your mass right now. Let's say you're talking about your gravitational force. It not only depends on the mass of the Earth, it also depends on your mass right now. So each of us here in this room, since we all have different test mass, all the force, each of us will experience different gravitational force. Agree? But what is the field strength at the chair where all of us are sitting? See, is it the same? So field strength is the same, but force is different, right now. So potential energy and potential also same relationship. The potential energy of each of us here in this room, we are all different because each of us did different amounts of work to climb the stairs to reach this room. Alright? For example, I would have done the most work, followed by Alex. Okay, example only lah. Alright, so then the least will be maybe Yusin. Okay. So she did the least amount of work. So therefore, she will have the least potential energy. But the potential at the chair where all of us are sitting are the same. It's the same like field strength. So then why do we want to find potential? Now, is field strength important to you? If you know the field strength 9.81 and you know your mass, can you find the force F equals mg? So it's very convenient one. If I say, if I ask Victoria, what is your mass? She said 50 kg.
No way.
Okay, 60.
No way.
45 lah.
No way.
No also don't bluff like you. Okay. No 40 45. Okay, so then let's say mass is 45. Mass is 45. Then the field strength is 9.81. When you multiply, you get your weight, right now? If I don't know the field strength at this point on in the room here, then I have to find your force by Gmm over r squared. So which is more convenient? By using the field strength times the mass, or using Gmm over r squared to find the force? Field strength times the mass, right? And because the field strength here is the same, I can find everybody's force very easily. Like Hamdan, for example, 60 kg. So 60 times 9.81, that's the mass. Like Yusin, 10 kg. So 10 times 9.81, so then you can get the force. Alright, so everybody's force can be found easily. Same thing with your potential energy and potential. If you know the potential in this room, let's say it's negative 20 joules per kg, like so Yusin will be negative 20 times 10. So potential energy is negative 200 joules. No? Just take the potential times the mass, right? Now this is some more important uses. For example, you know, like if you want to send a satellite into space, you know you need a rocket to carry it, right? So you need to know how much fuel to give your rocket. You cannot do try and error. If you don't have enough fuel, then you reach halfway and come back down, you wasted. If you put too much, also wasted, because you're going to discard the fuel when it reaches there. So what do they do? Now, if they know the height of the satellite where they want to launch, and you will learn later in this chapter, the satellites will have the same height if they want the same period. Example, there's this type of satellites that we're going to talk about called the geostationary satellites. And geostationary satellites are at a radius of 4.23 times 10 to the power 7 meters from the Earth center. So they're all fixed one. Why they want to put at that radius? Because they have exactly a period of orbit of 24 hours. So let's say you want to send a satellite there, but you don't know how much fuel to give. Now, because that point is a common point, we know the potential there, we times the mass of the satellite and the rocket, that gives us the potential energy. Right? If I know the potential energy, then I know how much KE to give it. Then I can calculate the fuel I must supply. So next time you want to launch another satellite into the same height, you know the potential again, you just times the new mass of the satellite. So very easy, you can find the potential energy. Alright, and then you work back your KE. So potential doesn't change with the test mass, just like field strength. Field strength in this room is independent of the test mass. Potential at this room also independent of the test mass. But force and potential energy is dependent on the test mass as well. So we say that force and field strength, force and potential energy are properties of the mass field system. Field strength and potential is the property of the field only. It doesn't depend on test mass. Okay? So you understand this,